Thank you, and good morning. I'm here to talk about two things, and I hope at least one of them is interesting to you. Number one is Apache Spark, which I'm sure everyone in the room has by now heard of. It's the new hotness in the Hadoop ecosystem. It's a new processing paradigm and has a lot to offer, I think, for the data scientists in the room as well. But I also want to talk about decision forests, which is a common and important algorithm in machine learning and data science, and one I think everyone should know a little bit about. So hopefully you're here to learn about at least one, maybe both at the same time. Let's begin. I want to start by backing up a little bit and talking about the roots of prediction, or where we got this idea of predicting some data from other data. And I like to go back to this picture. This was drawn by Sir Francis Galton in the 18th century, I think. He was studying the relationship between parents and children, specifically their heights. And he noted that tall parents have tall children, surprisingly. What he was really getting at, though, was that very tall parents have tall but not very tall children. And he called this regression to the mean, and we still do talk about regression to the mean. But interestingly, he tried to plot his data, and he plotted parents. I think he might have flipped the axes relative to what we're used to, but parents versus child height, and found there was a sort of linear relationship between the two, and the slope was less than 1. But I think this is really almost an example of an early predictive model, the idea that we could say something about the child's height given the parent's height as input. And this act of drawing a line to establish that linear relationship, we still call that regression for this reason, even though it really has nothing to do with regression to the mean or moving backwards or anything. So there is something interesting about this particular picture historically. Now, if you think about it, Galton maybe unwittingly was positing a black box. There's this chain of relationships, correlations, maybe causations, between this input and this output. We don't know what they are. I don't think he was trying to explain exactly physiologically why parents have tall children, but he thought there was a relationship there, and he showed the relationship. He tried to describe that black box in this linear relationship. And really, this is how most of machine learning or supervised learning thinks of the world. More particularly, there's a very common data set out there called the iris data set that people have used in research for years. And it's a data set that describes a bunch of irises or flowers and gives their measurements, their sepal and petal lengths and widths, and their species. And we think that there's some relationship between the two, that given some of these measurements, that causes or correlates with the type of flower that it is. And we don't know why. We don't need to know why in order to model that relationship or to describe that black box that connects those inputs to that output. And in fact, that's the magic of machine learning, that we don't actually have to understand the relationships. We can just try to model them and learn them empirically from data. This is an example from the iris data set itself. The data set's not important, but it's a good example of just about every normal machine learning data set out there. You have a bunch of examples of inputs plus output. In this case, it's 4 columns of numeric measures. These are the lengths in centimeters of the sepal and petal lengths and widths, and the species, the output. And this is the thing that we're trying to predict given the inputs. And again, we believe there's this connection between the two, and we want to discover what it is. Not discover it, but describe it and model it. And so given enough of these examples of the inputs and outputs, we believe we can learn how that black box behaves. And this is the essence of just about all standard conventional machine learning. Given enough of these feature vectors, we can build a model. This is an attempt to plot this data set. Now, it's really 4-dimensional, but here I think I've just plotted 3, or picked up a plot of 3 of the dimensions. So each point in space, 3 of its dimensions are determined by 3 of its inputs. And the color and shape is the output, or the species. And you and I can see that the iris setosa exists in a fairly distinct area of feature space. Intuitively, we understand that when the measurements are put a point over there, it's probably a setosa. And indeed, a lot of classic classification algorithms in machine learning are all about drawing lines, trying to figure out what's the dividing line between this data of one type and that data of another type. Because if we could draw this line effectively, we could effectively say that stuff over here in feature space is probably this type of flower at this type of output. And that's a form of predictive model. So if you've heard of logistic regression is really a linear model that's trying to pick some best line or really hyperplane in space that's dividing some types of the outputs from other types of the outputs. And if you've heard of support vector machines, it's also a linear model that tries to draw maybe a slightly better hyperplane that's maximizing the margins here between the classes in the line. And then if you've heard of support vector machines plus the kernel trick, that's an attempt to draw an even better line that's maybe not linear in the original feature space, so we can draw curved lines in space. And again, each of these, the idea behind each of these is let's just draw a better and better boundary between the outputs we're trying to predict to discriminate them. And this is good and this is powerful, but this is not the only form of algorithm or decision boundary we can construct to try to discriminate classes or outputs. And indeed, decision trees are not of this form, but they're still an interesting and powerful idea for classification. So I want to introduce them briefly. So to introduce decision trees, I want to give a quick toy example. So imagine you are a robot that works at a pet store and you need to know which pets are suitable for children, and you don't know why pets are suitable for children or not, but the owner has told you the following. You can measure the following attributes of the pets in the store, and you've been told in some cases that they're yes, suitable for children, or no, not. Now, I think you and I can kind of intuitively understand that a huge elephant is not a good pet, yes. Maybe a poisonous millipede is not a good pet, yes. But the robot doesn't know these things. The robot can only learn empirically on this data that we've given to it. Now, one valid approach, if you are the robot, is to try to come up with some rules of thumb based on this data that might discriminate the yeses from the nos. For example, you might indeed see that weight seems to matter. The very heavy pet seems to not be a good pet in these two cases. So maybe that's a good place to start. Maybe we try to make a decision rule based on weight. So we start there, and maybe this is the first decision rule we come up with. If it's over 500 kilograms, it's not suitable. If otherwise, it is. And that would be right in about half the cases, actually. That's not bad, but it's not really any better than chance. So that doesn't seem like a good enough decision rule. So we can make this more elaborate, maybe try a different threshold. Maybe 100 kilograms is a better place to begin discriminating, and maybe amongst the smaller animals, we need a further discrimination and another rule that based on color, maybe. So you can make a more elaborate decision process with several layers here and get more answers correct. For example, this decision rule, while still pretty simplistic, gets 7 of the 9 examples correct, and that's better, right? And you can imagine that with a couple more steps here, we could get 100% of the examples correct, which may or may not be a good thing, actually. We may overfit the data. But I think the process is fairly clear. We want to keep chopping up making decision rules and layering them in order to accurately reflect the input we have. And there's some process here by which we could do that. And the nice thing about the output here is it's fairly intuitive to read off. And in fact, this is a classifier. This is also a model of the relationship between 3 inputs and 1 output. So this is a valid classification algorithm as well. Of course, the question is, how do we build these trees? And that is, in fact, all of the complexity of decision trees. How do we pick the right tree? How do we know when to stop? Things like that. So for the curious, if you think about the rules that decision trees create, simple decision trees end up drawing decision boundaries like this in comparison. Axis-aligned boundaries. They keep chopping up space into halves in this case, via binary decisions, keep chopping up space recursively along certain dimensions. So that's qualitatively a different type of decision rule you can get out of decision trees than you can out of a linear model. And this has, in some cases, this is more powerful. This is a more powerful way to model decision boundaries. Here for illustration, I've built two different classification models. This is just in R. This is not Spark. On the left, we have a support vector machine model. On the right, we have a decision forest model. And in both cases, we're just going to build based on the iris dataset, which is so common it's built into R as iris. So very simple to do in R at this point. In both cases, we build a model, and it's a perfectly fine classification model. They both have high accuracy on this dataset. But interestingly, if you look at the model and try to interpret it based on its string representation, you'll find that linear models are a little bit hard to reason about. These are the support vectors, and they have a meaning, and we can understand them and maybe interpret them. But it does take a little bit of time to think about what this means. The meaning of this even changes based on what exactly you did in the support vector machine. So linear models are maybe not trivial to interpret, whereas decision trees are much more straightforward. You can almost read off the logic in plain language. At the top, the decision tree starts by asking whether the petal length is less than or equal to 1.9 centimeters. If so, I think this means predict the first class, the first of the three species. Otherwise, it looks at the petal width, and if that is small enough, it checks the petal length, and so on. So you could easily reconstruct the logic and explain to anyone what the logic is that led you to one decision or the other. And maybe as a botanist, you could evaluate whether these rules make sense, sure, but at least we can read them off and explain how the model is relating inputs to an output. And that's often also powerful, especially in think about finance or regulated industries where you do need to explain why your process approved someone for a loan or not. So this is a non-trivial consideration in modeling. Now, of course, as advertised, I want to talk about decision trees as implemented in Spark's machine learning subproject, which is called MLlib. At least the classic machine learning component is called MLlib. And it has an implementation of decision trees and actually decision forests as well, which we'll get to. So this is the part where we start to show what it means to build a real decision tree at large scale using Spark. For this example, I'm going to use a data set called the cover type data set, which is, by happy coincidence, also about trees and forests. It's 580,000 examples, each of which describes a piece of land, I think in Colorado in the United States. It has a bunch of features about that piece of land, like its elevation and slope, and I think humidity and distance to water, and maybe sunlight and so on. And it also has the type of forest covering that piece of land. Is it no trees? Is it aspen, spruce, etc.? This may or may not be interesting to us as a problem, but it'll make a good example. Can we actually predict, based on the attributes of the piece of land, what type of forest is probably growing on that land? This is, again, a reasonably well-known data set in the machine learning community, so it may make a good example as a benchmark as well. So let's look at the data. Well, the data is a bunch of feature vectors, examples. And as before, we have a bunch of inputs and one output. And I've printed an example here and formatted it in a particular way to make a few points about it. The first 10 columns, or 10 features, are numeric, and they're measures of things like elevation and slope, and I think distance to water and maybe to the nearest highway. I forget what they are. It almost doesn't matter. The next 4 features and the next 40 are actually, respectively, just 2 features, 2 attributes. These 4 describe the wilderness type. Is it desert or arid or scrub? I forget. There's 4 types of wilderness that a piece of land can be. So exactly one of these 4 columns is a 1, and the others are 0. So really, this is a categorical or discrete value that's been encoded as a series of numbers. And we'll come back to this point. But likewise, for these 40, this is actually one of 40 soil types. So there's 40 features here, but they're really conceptually 1 feature, because all of them will be 0 except for 1, which will be a 1. It's like an indicator flag. And last but not least, we have the cover type. This takes on 1 of 7 values, and these are encoded as a number from 1 to 7. So interestingly, there's really 3 non-numeric values here encoded in 2 different ways. such is life. This is real data. And to begin to work with it, we need to convert it into a form and a representation that the Spark MLlib implementations can consume. And for Spark, that's called a labeled point, which is really just a double and an array of doubles. The label is the output, and happily, it wants even categorical features encoded as a number, and we've already got that, okay? And then these are the rest of it is the feature vector, all the inputs, encoded as a vector, which is really just an array of doubles. So thankfully, that should be pretty straightforward. That's already how this data is encoded, actually. So this should be pretty straightforward to make objects like this out of the input. Let's do it. Maybe a little bit hard to read, but I'll walk through this. This is actual Spark code. This is using Spark's Scala API, and if it looks like regular Scala, it's because Spark really is at heart distributed Scala. So a lot of the operations that are actually Spark API calls here are going to look just like Scala collection API calls, and that's a good thing. Import some classes. First thing we'll do is open or get a reference to this data set, which may live on HDFS or your cluster's distributed file system. And in Spark, just about everything is an RDD, a resilient distributed data set. That's an immutable distributed collection of things. And in the case of a text file, that means Spark views that as an RDD of strings. So a text file is just a big collection of strings, one per line, right? So raw data is an RDD of strings. We're going to transform those strings into labeled points using a map here for every line, split on commas. So we make we tokenize it and we map each of those to a double. So now I've turned my CSV formatted line into an array of doubles. I'm going to take all but the last one and make a vector out of it. So this is my feature vector. I'm going to take the last one as the output or label and subtract 1 from it since Spark wants them to be 0-based, not 1-based. And there we go. I make a labeled point out of the label and feature vector. And that's my transformation process. So you can type this code into the Spark shell directly. No need to compile a program. And if you type that and you type that, you'll find that nothing really happens because there's been no action yet. We've just described a process that would transform data on HDFS into this set of objects in memory, but we haven't asked it to do anything yet. Before we go and do something with it and build a decision tree model, however, we're going to actually put aside about 10% of the data for testing purposes. That is, we're going to train the model on most of the data and hold back a little bit for reasons I'll show you on the next slide in order to test the model. Last but not least, it's interesting to note that we should cache the training data. This tells Spark that once you compute the RDD, do keep that result in memory in the cluster. So take those labeled point objects and actually persist them across the distributed cache that the Spark executors have. And this will be important because this process is going to access that data over and over. And if it's in memory, that's fast. And of course, this is why people say Spark can be a lot faster than, say, MapReduce, because it can use memory, so use more memory in order to gain speed. And that's a good trade-off in general these days. All that done, all that set up aside, then building the decision tree model is just one method call here. Decision tree train classifier, pass it the input data. We have to tell it, in this case, that there are 7 possible label values. And this we'll cover later. This concerns which values are categorical. And we give it a couple hyperparameters, which again, I'll explain in a moment. And the output is a decision tree. You can print it, and again, as in the R code, you see that we can sort of read off the logic. Here, given this API, it doesn't actually know what these features are. We haven't given them names, so all it can do is call them feature 0, 1, 2, 3. But again, this is elevation, for example. So the first decision is the elevation less than 3,042 feet, and so on. We could read off the logic and see this nested tree structure in the same way. So that's nice. So we've gotten a nice decision tree out of this. But of course, we didn't want to just build the tree to build the tree. We want to build the tree to make predictions. And looking at that decision tree, certainly we don't know whether it's a good model. Even I think if we're an expert in the field, I don't know that we could look at that and decide whether that is the best model. So we need some way to evaluate whether we've built a good model, whether this thing actually will predict other forest cover types from new data. To do that, we need some theory of evaluation. And that's why we held out some of the test data, some of the input data as a test set, because that's new data, or data the model's not seen before, for which we have the right answer. And so we could see how often the model predicts the same answer that we know to be correct from this test set. So that's what we're doing here. I'm going to make a method that takes in a model I've built and a test set, an RDD of labeled points. And for each one, I'm going to take that point and map it to the result of predicting from the model and the known correct answer. So the result of this function are tuples, or pairs, of predicted answer and correct answer. And Spark even has a little bit of support for automatically analyzing those results to get some metrics out. So that's what I'm going to return. And I'm going to use that on my model and test data, and then print out some of the metrics that come out from this evaluation process. So one thing I can get out of this is a confusion matrix. And a confusion matrix is effectively, these are correct answers by row. So here's all the 7 possible outputs, and the 7 possible predictions the model could have made. And ideally, the model's always right, and therefore, this is the count, the number of times that the correct answer was predicted to be such and such an answer. So ideally, only the diagonal would have the values, and everything else would be 0. That would mean in every case, the model predicted the correct answer. The correct cases are the diagonal counts here. And that's mostly true, as you can see, but not always. And the confusion matrix helps you read off some attributes of the model, like class 5 was never predicted for some reason. Don't know why, but maybe that's interesting. So in the main, it looks like the model's doing something reasonable, but it's not always right. You can see a number of errors here and here, for example. But maybe the one single interesting value out of this is the accuracy. How many times was the model correct? And that's about 70%. That's effectively the sum of the diagonal over the sum of everything here. Correct out of the total. 70% sounds all right. It's better than 1 in 7, I guess. But is that good? Could we do better? Is this better than random? And that's always, I think, a good way to think about these things. When you get a result, it seems okay. Benchmark it against something else, something simpler maybe. After all, if this is no better than random guessing, why bother with a decision tree model? Let's just make random guesses and do as well. So let's actually benchmark this against random guessing. And to do that, what we could do is look at our training set and count up the number of times each of the 7 outputs occurred, and then guess in proportion to those counts. For example, if class 1 was present in the data 50% of the time, then 50% of the time I would just guess that the answer is class 1. And some of the time that would be right, just like a broken clock is correct twice a day. It might be even correct quite often, who knows? So we can implement that pretty easily by counting. Here's another example of Spark in action. Counting the number of times each label occurs. So that's us taking the label out of each point and counting them up. And then just producing proportions or probabilities, if you will, out of that. So this is just counts divided by the sum of the counts. Yep. I do that for the train and test set, and then put them together. So we know the train probabilities dictate how frequently we'll guess one class versus the other, and the test probabilities give us a distribution of the actual correct answers in the test set. And from that, we could infer how often we'd be correct with this random guessing, and even make a pseudo confusion matrix here out of this process, which is going to be symmetric, of course. And it is worse. Random guessing, I guess not surprisingly, is not as good. It gets right about 38% of the time. So, okay, so out of the box, the decision tree algorithm is doing better than a very simplistic random guessing algorithm. So that much is good, so we must be doing something right. But can we do better? And yes, we can, for sure. So let's do better. Part of doing better is tuning the model. And I told you there were 3 parameters here I'd explain later. And these are hyperparameters to the model. They're called hyperparameters since they're not things the model learns, but things you have to give as parameters to the model building process itself. So whereas the model will learn which nodes to put where and which thresholds to choose, these are things we have to, are inputs to the model building process itself that we choose. Maximum depth, 4 here is easy to explain. That's the maximum depth that the tree will expand to. And you want to limit that because as you go build a deeper and deeper tree that chops up the data into smaller and smaller subsets, eventually you're only fitting noise. And that's not helping. And it's only helping you overfit the data you have in hand and is unlikely to help you make good predictions in the future. That and it takes extra time and it makes a bigger model, which takes longer to score. So this is the crudest way and the only way this implementation supports at the moment to know when to stop expanding. Now, you can also maybe look at when expanding the node seems to not help much because it doesn't gain you much information or decrease impurity much. And that brings us to impurity. So actually, maybe I'll explain the minimum bends first. In the initial example, I tried 2 different thresholds for the weight. Should I try a rule based on 500 kilograms or 100 kilograms? And in an algorithmic process, I'd want to try many more possibilities and pick the best one. And that is indeed a key part of what the decision tree algorithm does. It tries a bunch of node expansions and decision rules and picks the best one and then moves on through the tree. But what does best mean? I mean, yes, I can tell it to try 100 different values at every node, but which one is best? How do I know which threshold is the right one to choose out of those 100 that I try? And that's where the impurity measure comes in. Impurity is going to be the criteria by which we judge a split and its quality. And there's 2 possible values for the impurity measure. One is Gini impurity and one is entropy. I put up the formulas not because it's so important, but to illustrate that they're not actually that different. Even though their interpretation is probably quite different. The Gini impurity, I think you could most quickly view it as 1 minus the probability that a random guess is correct within that data set. So what does that mean? If the data set is very mixed and has a little bit of all of the outputs, then a random guess is unlikely to be correct. And so this value is high. And that's bad because we kind of want decision rules to break up the data into regions where the output is clear. There's only one type of label or output present in the subsets. So we do want lower impurity. We want a decision rule to take a high impurity set of data and break it into 2 subsets with low impurity. We could also use entropy as that criteria. Entropy is an information theory concept that measures, in a way, the mixedness of a set of things. And again, if you have a little bit of everything in a set that has high entropy, in a sense you could say that's because the predictability of the outcome at that point is high. The unpredictability is high. So again, we would love to make subsets from a decision rule that have low entropy, that have just one output or the other output, because then we'd be driving to a clear decision from the model. So in both cases, lower is better. And the formulas, ignoring this constant 1, which doesn't matter, they're both like a negative weighted average of something, in this case the log of the proportions, in this case the proportions themselves. So they're in a way related. But this is a bit of a sidebar. The question is which one's the better measure for this data set? And we don't know. We actually don't know just looking at this. So what do we do? I mean, how do we know which measure to choose, which maximum depth is right, or which number of bends to try? And this is a general problem in model building because models will have hyperparameters. And we don't know necessarily which ones are correct because the best value is going to depend on the data set. So the answer, thankfully, in Hadoop is just try them all, or try a lot of them. And in Spark, and specifically the Scala API, this is really easy to do. So I can write a triply nested for loop here. That's what this is in Scala. That's going to try all possible combinations of 2 values for these 3 hyperparameters. So I'm going to try both Gini, impurity, and entropy. I'm going to try depth 1, which should be very shallow, and depth 20, which should be very deep. And maybe I'll try building 10 bins versus 300 bins. And so there's 8 possible combinations here, and I'm going to build a model for each one of them here and evaluate its accuracy just like before, and return the 3 values I used and the accuracy at the end. And then I can just take those and sort them descending by this accuracy and print them out. So if you run this, I found when I ran it that I got about 91% accuracy with entropy as an impurity measure, depth 20, and trying 300 bins. That's not bad. I mean, clearly that's better than this combination, which is only 63%, and it's better than my initial guess of a Genie for 100, right? So just, I think it's kind of nice that just running this process, going and getting a cup of coffee, you can let this expensive cluster do the work for you and improve your predictability. And in fact, you could do this all day. You could try many more combinations. You could be smarter about this exploration of the hyperparameter space. But the point is that we can often throw hardware and raw brute force at a problem like this and have it do some work that's otherwise very, very complex or hard for us to know or guess. And that's the premise and promise of Hadoop. So I guess we might observe that, generally speaking, trying more values, more bins is better, which makes some sense, right? If I'm trying more possible thresholds, I'm more likely to get a better, best answer. And the expense there is simply that takes more computation. It takes 30 times longer to try 300 values versus 10. So that trade-off is more obvious, but the max depth and the information measure, that is not nearly as clear which one to pick. So it's nice to be able to appeal to brute force with the Spark and with Hadoop. And the nicer thing still is that, I mean, this is a parallel process. This will build in parallel across your cluster. But if you wanted to really make your cluster heat up, you could stick a .par in here somewhere in Scala and ask the driver program in Scala to evaluate all of this at the same time in parallel. So in parallel, build 8 models that are themselves parallel processes on the cluster. So you could easily fill your whole cluster with this process all at once, which is a good thing. If you've got the hardware, it's nice to be able to type a few characters and make full use of it to get an answer faster. So parallelism within parallelism. Can we do better? Yes, we can do better. To get better from here, we might need to not just apply brute force, but think a little bit through the process and make some improvements to our data and our representation. So that will also give us a win. And I want to come back to this idea of categorical variables. So as I say, really the output's a categorical variable. It's a cover type. There's no ordering to it. There's no such thing as spruce being greater than aspen or spruce being 1 less than oak. But we've encoded it as a number. And also, there's 2 other values in the data set, the soil type and the wilderness type, that are also not ordered values, but we have to represent them as numbers, or we've had to. And the way they've been encoded in this data set is called one-hot or one-event encoding. The practice here is to take a set of a categorical value that takes on n possible values and encode it as n indicator variables that are 0 or 1s. So for example, if I had a categorical value that took on 3 possible values, cat, dog, and fish, I could encode that as 3 features, exactly one of which was 1 and the rest of which are 0. So you could think of this as like an is cat, is dog, is fish feature. And it turns out that's a reasonably principled way to encode non-numeric data as numeric. For most algorithms purposes, that's a pretty good encoding. The only downside is if this has a lot of distinct values, this blows up and becomes pretty hard to manage. In this case, it's pretty reasonable. We had one value with 40 values, but that wasn't so bad. Now the thing is, this process is necessary if you're using an algorithm that can't consume categorical values directly. For example, the support vector machine. Decision Force can consume these categoricals directly, or they have a principled way to evaluate rules based on categoricals without this encoding. So in a way, this is not optimal for a decision tree. So we can undo this encoding and then try again and see if that actually helped with a different representation. So conceptually, we're going to collapse these 4 and these 40 features down to 2. This is going to become the index that was a 1 in this set of 4, and this is the index that was a 1 in this set of 40. So here we're again still representing these non-numeric values as numbers, so we'll have to be a little careful to realize these aren't numbers, but we can tell the decision tree algorithm to treat those as categorical values and proceed accordingly. So that ETL process is still pretty straightforward. Split the line. We're going to chop off the 4 and 40 values, figure out where the 1.0 is, and add those back as additional features on our feature vector, and proceed as before to return a labeled point. Easy. And then try again. The only difference here is we're telling the input that that 10th feature and that 11th feature are not actually numbers, they're categorical values, taking on 4 and 40 different values respectively. So you have to tell this particular implementation about that ahead of time. Other than that, it's the same. We can run the same hyperparameter selection process and come out with new answers. So in this case, the best result was about 94% accuracy with similar settings, I'd say. I tried some different values here, depth 30, 300 bins. So that's not bad. I mean, it seems clearly like we're getting better results from this process. And I guess the reason is that we're losing less information by collapsing conceptually one value down to one value and letting the algorithm treat it accordingly rather than encoding it and sort of obscuring the data. So data representation does matter. And this is another argument for decision trees, that they can consume these non-numeric features directly. Can we do better? Yes, we can still do better than this. Now, this is where decision forests come in. So as you probably guessed, a decision forest is a bunch of decision trees put together. And in particular, we're going to talk about random decision forests. Now, to set the stage for this, I want you to think, take a guess. Don't tell me, don't tell your neighbors. How many black cabs operate in London? Think for yourself. I don't know. I took a guess, like you are right now, and I was wrong, of course. But then again, most people are wrong. But we all probably made some educated guesses. So the real answer is about 19,000. I guessed about 10,000. Maybe you got closer than I did. I asked around our office and got some really startlingly bad estimates of the number of taxis in London. But interestingly, if I took the mean of all the guesses, the mean was, well, closer to the correct answer than my answer was. And in fact, it was closer to the correct answer than most answers were, in fact. So even though lots of people were quite wrong, on average, people were reasonably right. And this is the so-called wisdom of the crowds. If we combine some partially educated guesses, we end up with a better guess overall. And so this is the phenomenon we want to leverage in machine learning when we talk about ensemble techniques, where we are actually putting together many classifiers that may have different opinions about the right answer and producing one answer out of that that's maybe better than in the individual classifier's output. So let's see if we can use this phenomenon to improve on decision trees. Yes, so decision forests leverage the wisdom of the crowds. That's the key takeaway here. Now, the problem here is everything I've described so far is deterministic. So if you give this algorithm the same data and same hyperparameters, you'll end up with the same tree every time. And that doesn't help. It doesn't help to have 100 copies of the same tree giving a prediction because they're all the same. It's as if I have just one tree. What we really need is a diversity of opinion here. We need a bunch of slightly different trees giving slightly different opinions, good guesses, good predictions, but maybe slightly different ones that we can average together into a better overall prediction. So how do we do that? How do we actually get different answers out of the same algorithm and same data? Two things. Number one, we can handicap each tree a little bit by showing it only part of the data. So for example, you could make 10 trees, each of which look at a different 90% of the data, and for which a different 10% of the data is held out. So each individual tree is going to be a little bit different since it's seeing different input. It's going to be a little bit worse off than a tree that looked at all the data since it has less input. But strangely, the average guess over all those 10 trees is going to be better in general than one tree built over all the data. That's a powerful idea. And this is where the idea, the motivation for random forests comes in. We could also do the same thing, but with features. You could have different trees look at different subsets of the input and make different predictions based on that. For example, this tree could look at just the elevation and the slope and so on. This one might be looking at soil and wilderness type, and they would get different answers indeed. But maybe overall, the combined answer is indeed better. You can do both. You can slice it up both ways. In fact, you can slice it up to some degree randomly, which also generates some degree of difference in the outputs of the trees. And this phenomenon makes decision forest, the building process, especially nice for Hadoop. Hadoop is fundamentally a data parallel paradigm, where we have to live with data distributed all across a cluster and in a world where it's relatively expensive to move data around. So we need to do small operations on small subsets of the data and combine the answers at the end. And that's exactly how decision forests work. The idea is to build weaker trees on small looks at the data independently and then combine them into one ensemble or forest at the end. So that's another reason decision forests are nice in a data parallel paradigm, like Hadoop. So if we do something like this, we will find we get different trees, not just different thresholds throughout the tree, but totally different structures, trying different features, making different predictions, et cetera. So we will get a diversity of opinion from these trees, and we can make hundreds of them, or even 1,000 if we want. And then to make a prediction out of all of them, we are simply taking a majority vote, for example, asking each of the trees for a prediction and predicting the one that occurs most frequently. Pretty simple stuff. We can thankfully do that in MLlib as well. This is also implemented in Spark. Very similar, except that there are two new parameters now. One is the number of trees to build, and another is called the feature subset strategy. This is really how it chooses how many and which different features to randomly try at each level. And to some degree, it also controls how the examples are apportioned to the trees. So in a way, this controls how different pieces of the data get fed to different trees. For purposes here, we'll leave it at auto, but there are some other settings. And the rest is the same, though, same hyperparameters as for the decision tree model. And if you go through the same process and try a bunch of hyperparameters and try different numbers of trees, you can get pretty easily better accuracy than we had last time. I got about 96% accuracy with the same process, with just a couple hours of tuning on my cluster. I imagine if you tried a little harder, you could get 97%. I don't know. I think the best algorithms I've seen for cov type end up with maybe a 2% error rate or so. So this is pretty close to state-of-the-art for this particular data set. That's not bad for a simple algorithm that's implemented for you, that you can use brute force and a bunch of cluster power to tune for you and get nearly state-of-the-art results. And indeed, this is random forests are generally a pretty competitive algorithm for a large range of problems. So definitely worth knowing about, definitely worth learning about in the context of Hadoop and Spark. Now, that's not the end of it, though. If you've gone to all this trouble of preparing your data and making labeled points, you can easily try other algorithms in MLlib. For example, there is an implementation of the support vector machine or logistic regression. And they take the input as the original input we showed is something you could easily feed into these algorithms as well. And you could easily put those into an evaluation loop as well and see what their accuracy is like. So that's another nice thing about using MLlib. It does have a fairly standard and cohesive set of implementations with the same sort of input and same sort of outputs, so you could easily compare and contrast them. Another fun thing about Spark is that it's not just for ETL, it's not just for machine learning. It has a streaming component called Spark Streaming, which is Spark as applied to a stream of data coming off of a message queue like Kafka, for example. And whatever you do in Spark MLlib can be used within Spark Streaming. So that decision tree model could be directly reused in a Spark Streaming job that would maybe score data, make predictions on data as it arrives in the cluster. Now, maybe that's not so useful for forest cover type, but it might be useful if your model is predicting fraud if it's detecting anomalies in sensor data, for example. So it's nice to be able to just directly port that code, move that model into a streaming job with no change or rewriting. And maybe it's also worth noting here at the end, to tie it back to the beginning, that random decision forests are not just classification algorithms. We've been using it as a classifier here to predict a discrete categorical value, but they can also be used for regression, which means predicting a continuous numeric value. So you can predict numbers as well as categories with this exact same technique. And that's also implemented in Spark MLlib. Worth knowing. That's all from me. Thank you very much. Are there questions, objections? Sir?
You showed that a decision tree, a normal decision tree, is more explanatory than, for example, support vector machine or a logistic model. How about random forest? Because it seems to me that it's not really explanatory anymore, right?
So a random decision forest is really just a bunch of decision trees. So it's more complicated than that you're digging through a bunch of these trees, not just one. But underneath, they're all just the same decision trees inside a forest.
But do you then have any, does this have any implications, for example, using this in practice? Because, for example, I work for an HR company in the Netherlands, and I know that when we have matching and searching models, then people find it, have mental difficulty to use it when they don't know what the results are coming from. Is this harder for decision forest than this simpler decision tree model?
I think it's probably the interpretability of the model is about the same between a decision tree and decision forest, since the forest is just many trees. But you're right, that's exactly the kind of case where the trees are nice, because often people either have to or just want to understand how the model's thinking, and you can read that off directly in the case of a forest or trees.
Yes, and then one final question. How do decision trees and random forest in general compare to, say, for example, support vector machines in accuracy, precision, recall, things like that?
In general, how does this perform versus SVMs? I don't think there's one answer to that. I guess on interpretability aside, decision forests have some advantage in that they can do multi-class pretty easily and consume categorical variables. That said, generally speaking, decision forests are a brute force approach, which is okay in some cases, not in others. They tend to struggle a little bit with a very large number of features, and SVMs have some tricks that make a very large number of features work well. So I think they have just different properties. There's no one answer.
Thank you.
Question here? Yes, sir. So the question is, when I build a decision forest, am I using the same hyperparameters for every tree? Yes. So I'm making one call here to train the classifier, and I'm giving it one set of hyperparameters. I can build different forests with different hyperparameters, but within one forest, that's constant. The features and examples that you look at are different across the trees, though.
Okay, and will there ever be an option to change hyperparameters within a forest, or isn't that an...
Would you ever want to use different hyperparameters within one forest? It's not crazy. I think it's probably not that important. You would generally want to have one consistent measure within a forest. Although I guess decision forests are an example of ensemble learning, where you don't care what the individual classifiers are, you're just averaging their results. So it wouldn't be crazy to combine two forests that were built in different ways with different hyperparameters and average all their results. Maybe not as important or not as helpful, but there's some use for it. But no, this doesn't exist in this API.
Okay.
There's a question in the back. Right, so how is performance affected by the size of the forest?
Yes.
So certainly the prediction time grows linearly with the number of trees, since you have to run each example through all of the trees. You can do that in parallel on the plus side. It also, of course, depends on the depth of the tree. But that's less of a factor, since that's kind of, that time grows logarithmically with the number of decision nodes, and that's not as generally a problem. So generally, I would describe decision forests as fairly fast to score. They're not as fast as a linear model, which is just doing a dot product maybe. But generally not really a problem. Yeah.
I have a question. Would a similar approach could be applied to not to trees, but to a linear model? So
Sure.
would that deliver some advantages, in fact?
Could you put together an ensemble of linear models? Yes, definitely. So decision forests are really just ensembles for decision trees. You can make an ensemble of support vector machine classifiers as well and would see a similar effect. Yes, I think that's done as well. I think that the benefit of ensembles is maybe more pronounced in decision trees, or somehow is a nice fit for the way decision trees work. But there's nothing specific about that idea that's specific to decision trees, yes. One more, okay.
There is any relation between the number of features and the number of trees that should be used?
Okay, is there a relationship between the number of input features and the number of trees that should be used? That's an interesting one. So I suppose it depends on how many different features each tree looks at. Because generally speaking, each tree will not consider all the features. So for example, for a classification problem, often each tree will look at about the square root of the number of features. I think that's the default in R, and most people have just followed that. So given that, I suppose if you only had a couple trees, and a large number of features, you would probably end up not ever looking at some of your features, just randomly, because only a few are chosen. So I suppose you want to have enough trees that you suspect you've used all your features at least once, on average. One more?
Was there any occurrence of a deadlock? Because there can be a chance of contradiction of, when you combine different trees, there can be contradiction of different subset of features. So, was there any deadlock? I mean, it was running for long, and was there predictability reached, or did you face anything like that?
Is there a possibility of deadlock in the implementation?
Did you get any deadlock? I mean, because when you compare between different trees, there can be a contradiction, right? Because different decisions by different features in one tree can be different from another tree. So.
Oh, do the trees disagree? Yes, absolutely. So hopefully the trees, generally speaking, agree on a prediction, and that's your final prediction. Okay. But they won't all agree in general. I guess the nice thing about that is you could return to the caller not just one answer, but a distribution of predictions. 70% of the trees say it's class 1, 20% say it's class 2. And in fact, even the trees themselves can give you a distribution over the categories, and you can average those distributions. So yes, there's certainly, the trees will arrive at different answers sometimes, but that's fine. That's to be expected. Thank you very much.